electron configuration. But if we look, we'll notice kind of like we go down and also we go up and down, 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 and up, and down, 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 and up. And we get this, every single time we hit this S block, we have a shift up in energy. So that might be one thing you notice. If you paid attention to the atomic number, you probably figured out that this is hydrogen and helium. And then this is lithium and beryllium, followed by the next 6 elements going on to neon, and then up again. Okay? So it might be something else you notice. You might also have noticed that these red dots here, it says transition metals. Well, that's our brown block that we've been kind of avoiding a little bit. And they just seem to fit in right here. We're going to talk about the significance of that later. So take a moment, and what do you notice about this graph? A few things that are happening here. Again, we have our S block, and this is electron affinity. And so I start high and then I go low. Next one up, high, low. And then we get a 1, 2, third one's low, 4, 5, 6. And so there's something going on here. So let's check this one again. 1, 2, third one's low, 4, 5, number 6 is low. Okay. And then I have, so here I have 1, 2, 3. I'm the fourth row in. Here is potassium and calcium and our transition metals. 1, 2, 3, 4, 5 is low, 6, 7, 8, 9, 10 is low. So something's happening. We're hitting the halfway point. This one is on electronegativity. And here we go again. We've got a dot. 1, 2, follow with 6 blocks. Then we have separation, 1, 2. And then also we have transition metals. What are you noticing? What do you see? First, ionization energy. So even though you may not know what that is, just look at your data. Hydrogen, helium, and then I have a shift down. 1, 2, 3, 4, 5, 6, 7, 8, and then down. 1, 2, 3, 4, 5, 6, 7, 8, then down. We have our 10 main groups on here, and we've actually put some of the trends that we're looking at on here. But now we need to look at it a little bit differently. So we talked about that the periodic table, it's a tool, and it's got a wealth of information on there for us. And so now we're going to add another level of information on there, what's called sp, d, and f orbitals. And so you are going to take your periodic table, your new one, and you're going to color it up just like I did. Your colors don't matter what they are, just get them colored. Make sure you put in a key. And then make sure you notice that for the s and p orbitals, the numbers all stay the same as the row. Okay? But if you notice your transition metals, they're actually shifted up an energy level. So I want you to mark on your periodic table 3, 4, 5, and 6. And then on your inner transition metals, mark them 4 and 5. So this is just another way of looking at what we've already talked about. Again, we need to mark our transition metals 3, 4, 5, and 6. Inner transition metals 4 and 5. Next thing up for you to work with a little bit are what are the guiding rules for electron configuration. So what does this mean? So we're about to start on this journey of feeling electron orbitals. And we have some guiding principles that we've already been working with, but I didn't tell you what the names were. The first one is called the Aufbau principle. Aufbau is German and it means to build up. So we start at hydrogen and we build up. Okay? Electrons are added one at a time, just like your protons are. And so they're added to the lowest energy orbitals available until all the electrons in the atom have been accounted for. The second rule we mentioned when we did our study over atomic history, which is Pauli's exclusion principle. And that tells us that there is a max of 2 electrons that each orbital can hold. And it also tells us that to occupy the same orbital, 2 electrons must spin in opposite directions. And so when y'all did your Bohr model and your Lewis dot, I had you pairing them after we hit the halfway point on that shell, which at that point was only, we were only feeling to 8. Okay? And I talked to some of y'all about thinking of it as being like magnets. So just like magnets are attracted to one another by opposite spins, so are electrons. In all honesty, we think of electrons in many ways like what we think about our planetary system. These electrons are not only orbiting around the nucleus, but they are also spinning on their axis, which is creating a magnetic field, and thus creating the attraction. Okay? So we use the world around us to explain that which we can't see, and we have good evidence for these rules. The last rule is Hund's rule. It says opposites attract. So electrons occupy equal energy orbitals so that a maximum number of unpaired of electrons results. And so we're going to look at what that actually means. Another way of representing what we're fixing to do is this Aufbau diagram. And so it just shows we're going to go to 1s, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so forth. Here's the thing, and this seems to help students. Remember the game Chutes and Ladders? Okay, this is my starting position. Whatever element I have you feeling to, that's your ending position. So let's just say that we're going to phosphorus. Well, the only way I get to phosphorus is I've got to go all the way through row 1, which is an S block. Once I hit my noble gas, I swing on down to the next row. Then I go across row 2, and swing on down to row 3, And just like in the game Chutes and Ladders, each one of these blocks represents a position on the board. I have to go through each one of the blocks to get to phosphorus. Okay? So that's what we're doing. All right, let's do this. So the first one we're starting off with is hydrogen. And hydrogen has 1 electron. It is on row 1, 1 block in, and then the S block. So this is an Aufbau diagram. The arrows represents electrons. So I'm going to draw 1 up arrow to represent the 1 electron of hydrogen. Then I'm going to write the electron configuration. So I write, 1 S, and I have 1 arrow, so I wrote an exponent of 1. The 1 must be written. It is not understood to be there. Okay, let's do boron. So I look on my handy dandy periodic table here. I'm going to find that boron is over here in the P block. It's on row 2, and it's 1N, okay? For some students, what helps them is to find their endpoint first. So 2P1. I'm going to put one arrow into P, 2P1. Now, in order to get to 2P1, I had to put in an up arrow for hydrogen, down arrow for helium, up arrow for lithium, down arrow for beryllium. If I have atomic number 5, I have to have 5 electrons. 1, 2, 3, 4, 5. I have 5 arrows. So now I'm going to write this expression as, I start with my Lewis, 1s2, 2s2, 2p1. 2 plus 2 plus 1 is 5. This one is correct. So here's chlorine on my periodic table. It's on row 3. It's in the P block. And now I'm going to count blocks just in the P block. 1, 2, 3, 4, 5. Which means I'm ending with 3P5. Okay, let's do this. Let's do our endpoint first. There's 1. Then I go to my next block, 2 and 3. So that we saw this trend where you had to hit the halfway point first, then your energy decreases. So based on that evidence, we know that we got to put 1 electron in each box first. Now I go back and I double. 4 and 5. So I have my endpoint done for chlorine. Now, all these other boxes down here have to be filled. So again, I have an up arrow for hydrogen, down arrow for helium, up arrow for lithium, down arrow for beryllium, up for boron, up for carbon, up for nitrogen, then back to the front, down for oxygen, down for fluorine, down for neon, then up for sodium, down for magnesium. If I count my arrows, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, I have 17 arrows. So now I'll write the electron configuration starting with 1. So 1s, there's 2 arrows, so I'll do 2. 2s, 2 for 2 arrows. 2p, 1, 2, 3, 4, 5, 6, which is also the max for the P block. Then 3s and 2, and then 3p5. Your numbers do have to be written in order, and it's always SPDF. 2 plus 2 plus 6 is 10. 11, 12, 13, 14, 15, 16, and 17. So everything is correct on this. Now you try the rest. See what you can do.